Kinetics is about studying rates of reaction, what things affect how fast a reaction is going. Gives us a clue to this thing called, well, what we call mechanism. When you look at a balanced equation, you get no clue as to what the pathway is in terms of how the reactants turn to products. I mean, all you get is something conforming to the law of conservation of mass. How many atoms are going in, how many atoms are coming out. So when you study rates of reaction, you're also studying that pathway that the reactants have to go through in order to get to products. Factors that affect rates of reaction. Well, first of all, guys, we have to remind ourselves, well, we have to reintroduce the idea of kinetic molecular theory. I mean, this was the whole thing we had between why gases behave the way they do, right? Particles are in motion. If a particle hits the side of the container, it is a reason for why that container has pressure. Well, with kinetics, it's about the molecules hitting molecules. And if they hit hard enough and in the right way, do we get a reaction? Do we get a rearrangement of bonds and a chemical change? So things are going to affect, in essence, what's going to affect rates of collision? Well, the first thing is the physical state of the reactants when they come into contact with each other. Meaning, hey, with some molecules especially, you have to have a collision in a particular orientation, otherwise you don't get an effective collision. So things like that slow up rate of reaction. If I have to wait around for a collision to occur in the right orientation, that's going to make the reaction go slower. So do you have that with a reactant? Being homogeneous means gas phase and liquid phase. The more mixed up the particles are, the more effective the collisions, right? So whenever we have a solid interface, that's going to not allow collisions with anything but the surface area. So that's going to change the rate of reaction. So when you have things in the gas phase, it's really about concentration. The more concentrated the reactants, the more collisions, the faster the rate of reaction. Temperature, as we know, if you want to speed up a chemical reaction, heat it. The higher the temperature, the more collisions you get, and the harder the collisions you get. The harder the collisions, the more likelihood of having an effective collision. Presence of a catalyst. We'll get into this in more depth later on in this section, but a catalyst is a way of changing the mechanism so that we get more effective collisions. And a catalyst goes into a reaction but comes out the same way it came in. So it's not a reactant, it's not a product, it's outside the reaction. Homogeneous reaction literally means reactants being in the gas phase or reactants being in the liquid phase. And in that situation, it's going to be an issue of concentration. The higher the concentration of the reactants, the more likelihood of a collision. Heterogeneous reaction refers to things in the solid phase. So if you're in the solid phase, it's a surface area issue. So the more surface area we can create with a solid, the more collisions we can get between the reactants. All right, so how do you define rate of reaction? Well, there's a time component. So how fast does a reactant disappear over time, or how fast does a product appear over time? So change in concentration over change in time. Delta C over delta T. Sometimes you see a positive in front of the change in concentration over time. That's referring to how fast the products are appearing. Sometimes you see a negative time and a negative sign, and what they're referring to there is how fast the reactants are disappearing. So we have a reaction here, bromine reacting with formic acid to form hydrobromic acid, or bromide ion, H plus ion, and carbon dioxide. So how is the rate of reaction expressed? Well, there's two ways. we can use algebra or we can use calculus. When we talk about average rate of reaction, we're talking about algebra. The difference between 2 points and how the concentration is changed. So after 50 seconds, what's the difference between the concentration where you started and where you ended? After another 50 seconds, what's the change in concentration, and so on. So take the change in concentration between 2 points, divided by the change in time between those 2 points, and that'll give you the change in rate. Again, the negative sign here is referring to the fact that bromine is disappearing. I don't know, it's kind of silly. There is no such thing as a negative rate, right? So it's again, the negative sign is just for how fast the reactants are disappearing. So we get a curve. When we plot this data, change in concentration of bromine versus change in time, we get a curve, which implies that, hey, as the concentration of bromine changes, so does the slope of this line. So if I take the change in concentration between 2 points after 50 seconds has gone by, what I'm basically doing is taking the slope of the line between those 2 points. In essence, we're pretending that this curved line is straight between those 2 points, and this gives me what's called average rate. All right, so it's an approximation. You're pretending that the line's straight between those 2 points. If we take the slope of the line between the next 2 points right after the next 50 seconds, notice that the slope of the line is getting shallower. So what this implies is that the rate of reaction is going slower. So as the concentration of bromine goes down, the change between the concentration and the change in time is the ratio is less. So we get a shallower slope, which means a slower rate of reaction. There's a relationship between the stoichiometric coefficients and how fast a reactant is disappearing versus how fast another reactant is disappearing, or how fast the product is appearing. So depending on what you pick, you're getting a different rate. So we picked the rate of how much bromine was disappearing, right? So after a certain amount of time, the change in concentration over the change in time was 3.8 times 10 to the minus 5 moles per liter seconds. So how fast is H plus appearing? Well, we just go to the coefficients for that. So for every mole of bromine lost, you're making 2 moles of H plus, which means that H plus is appearing twice as fast as bromine is disappearing. Average rate. We're using algebra. The way algebra works is you take the difference between 0.1 and 0.2 on the curve, and you get a straight line slope. In order to get an instantaneous rate, I mean, what's the rate of reaction at a particular point in time during this reaction? We have to use calculus. And calculus gives us a line perpendicular to the curve at that particular point. So this is what instantaneous rate is. So what is the rate of reaction at 100 seconds? What is the rate of reaction at 200 and 300 seconds? So I can do that by taking the derivative of the line perpendicular to the curve at that point, and I can get the slope. So this isn't a calculus course, but we do have to understand that this is where this is coming from when we talk about instantaneous rate. So at any point during the reaction, what is the rate of reaction at this point in time? That's what instantaneous rate is. All right, instead of plotting the rate of reaction versus time, now we're going to plot the rate of reaction against concentration. All right, so when we talk about this reaction, it's strictly about the concentration of the bromine in terms of rate of reaction. As the concentration of bromine goes down, what we've seen with this data is the slope of the line is getting shallower and shallower, which means the reaction is going slower and slower. So when I take a plot of concentration versus rate of reaction, I get a straight line with a positive slope. K represents the slope of this line, right? The change in rate over the change in concentration. So if I multiply both sides by concentration, I get what's called a rate law. A rate law equates rate to concentration of a reactant during the reaction. So if we divide the concentration into the rate at any point in time, we get the same number every time, right? This is the rate constant. moles per liter second in this case. That's going to equate moles per liter to rate. Oh, I'm sorry. It's moles per liter second is the rate. The rate constant in this case is going to be liter moles per second. All right, so rate and concentration. So you do experiments to figure out what the effect is, for example, of fluorine on the rate of this reaction, or chlorine dioxide on the rate of this reaction. So we start off with a certain concentration of fluorine, a certain concentration of chlorine dioxide, and we measure the instantaneous rate at this particular point in time. And then we change the experiment. We start a new experiment, except this time we hold the concentration of one reactant constant while changing the concentration of the other. So in this reaction, as I quadruple the concentration of chlorine dioxide, I quadruple the rate. So there's a relationship between concentration and rate of reaction here. Between experiment number 1 and experiment number 3, I'm holding the concentration of chlorine dioxide constant, but doubling the concentration of fluorine. Well, that doubles the rate of reaction, which also shows an effective concentration of rate of reaction. So this is where our rate law comes from. It comes from experimentation, changing the concentration of the reactants and seeing how it affects the rate. So the way we read this rate law is it's a direct relationship between both reactants. Doubling the concentration of the fluorine would double the rate of reaction. Doubling the concentration of chlorine dioxide would double the rate of reaction. K is a constant that equates these concentrations to rate. All right, this is called a first order relationship. I don't put the 1 in there when it's a first order relationship, but it means that without the 1 there, concentration of fluorine times the concentration of chlorine dioxide, first order with respect to the one reactant, first order with respect to the other. But if I double the concentration of both reactants at the same time, I'm not going to double the rate of reaction. I'm going to square it. I'll have a quadrupling effect. So this is called a second order rate law overall. So double the concentration of the reactants quadruples the rate of reaction. Notice it has nothing to do with the stoichiometry in the balanced equation. The balanced equation is just to conform to the law of conservation of mass. When you talk about rate laws, what effect the concentration of the reactants is having on the rate, it's strictly determined by experiment. Another reaction. So we have an anion reacting with iodide to form sulfate and I2 minus. So I have a first experiment, right? A concentration of both reactants. I do a second experiment, but I hold the concentration of the one reactant constant while halving the concentration of the iodide. Well, this halves the rate of reaction. So again, what this shows us is we have a first order relationship with respect to iodide. Halving the concentration halves the rate. Hold the concentration of iodide constant in the second experiment compared to the third. Double the concentration of S282 minus, and it doubles the rate. So this is first order with respect to S282 minus. So again, first order with respect to both reactants, second order overall. Doubling the concentration of both reactants would square the rate of reaction. Determined from experiment, not from the equation.